Another useful tool is small signal AC circuit analysis, which lets us figure out how our circuit behaves with different frequency signals. The AC analysis calculates our circuit's frequency response by injecting a sine wave at a particular point in the circuit, and then we can use voltage probes to see the response of the circuit at that point, the point of each voltage probe, over a whole range of frequencies. Let's see how that works. Coming over here to a circuit sandbox, what we have is a voltage source feeding a small resistor network, in this case a resistive divider. To that we've added a 1 microfarad capacitor, which will change the frequency behavior of the circuit, as we'll see in a moment. Let's start off here by doing a transient simulation and look at the resulting waveforms. In this case, with the capacitor present. So we're going to do a 20 millisecond simulation, transient simulation at 100 Hertz. So we'll see two oscillations of the source waveform. As you can see here, we see two oscillations of the sinusoidal voltage source. We can also look at the response now, the transient response of the middle node of the voltage divider, which we can see is approximately a quarter of the voltage, which is what we'd expect, although it's a little less. And in fact, it's down. We expected 250 millivolts, and in fact, we only see 227 millivolts. And you can see, in fact, that the peak of the waveform at the voltage divider is a little shifted from the peak of the battery waveform. So this is different than a straightforward transient analysis of a circuit without the capacitor. So the capacitor has, at 100 Hertz, we can see that the response, the capacitor has changed the response to be somewhat less in amplitude and somewhat shifted in time. Now let's see what happens. Let's just save this guy for a second. Let's see what happens if I come over here and I ask for the same analysis, but this time using a 1000 Hertz waveform. So I'm going to do another transient analysis. And let's compare the two. Well, obviously we have 10 times the number of oscillations, but if we look at the red waveform, one is we can see that it shifted almost 90 degrees relative to the oscillations of the blue waveform, in other words, what's coming out of the voltage source, and that the response is actually considerably smaller, and now we're only getting about a 50 millivolt amplitude signal across the capacitor, whereas over here we got a 227 millivolt signal. So in fact, as we increase the frequency of the test waveform, we can see that the response is getting smaller and smaller and smaller. The AC analysis tool lets us determine that directly. So what I'm going to do is close the transient analysis windows and come over here and add a name so I can refer to it later to my voltage source. And now when I ask for an AC analysis, I can say, look, I like it with respect to the voltage source named SRC, and I want to look at the frequency response of my circuit between 10 Hertz and a gigahertz. If I click OK, I get two plots. One showing me the magnitude of the response and the other showing me the phase. It's a log plot in both directions. We're plotting the response here of the magnitude in decibels, which is a logarithmic ratio, or the log of the ratio of the amplitudes of the test signal and the response signal. And over here, the frequency is plotted in a log scale. So 100 Hertz is down here at 10 to the 2. And at 1000 Hertz, we're at 10 to the 3. So what the AC analysis is doing is if we look at the magnitude plot, we can see that at 100 Hertz, we're down approximately 12 dB, a little bit more, which is about 23% of the original signal, which is what we expected, about somewhere around 230 millivolts. And if we looked at